What's going on, class? Welcome to another lecture. Hope you all are doing well this morning, right now, or evening, or whenever you're watching this. I'm not going to assume it's morning, but let me go ahead and tell you that today we're going to be jumping into chapter 12 of our book. And more specifically, chapter 12 deals with the deflection. Hope my pen doesn't run out of ink today. The deflection and slope of beams. The deflection and slope of beams is what we're going to be talking about today. And here's the thing, right? We're going to be getting into a process that is going to be necessary for you to be able to know how calculus applies to a lot of things we're doing here in mechanics and materials, and know how to work and manipulate equations that help you find the deflection and the slope of beams. So I want you to pay close attention to things that are happening. Sometimes it can be tedious. It's a lot of room for error, as is with most big problems, right? But in this case, I want you all to really focus in and really make sure you get this. And I'm going to start really quick with this concept known as rho, this Greek letter of rho. And what rho represents is the radius of curvature. Make sure I spell that, curvature, the radius of curvature, right? Rho is the radius of curvature. So what is meant by that is if a beam was bending like this, let's just say a beam was bending, right? This is an exaggerated curve of how a beam could bend, right? For whatever reason, it's bending upwards. If you were to imagine that this beam was part of a much larger circle, all right? So let's just imagine, right, that's just part of a big circle. That imaginary circle would indeed have a center, right? Right? If the bending beam was a part of a larger circle, that imaginary circle would also have a center. Well, that center of that circle would also give you a way to determine a radius of that circle. That radius is what we call the radius of curvature, right? So the radius of that massive circle, that imaginary circle for which this exaggerated beam bending beam is a part of, is denoted by rho. And so there's a relationship I want to show you that correlates rho to the moment and the modulus of elasticity and moment of inertia of a particular beam. And that relationship is as such: 1 over rho looks like a P sometimes when you write it, is equal to the moment over EI, right? So the radius of curvature, which is this rho, is 1 over the radius of curvature. The inverse of it is equal to the internal moment. This is internal moment, to be more specific, internal moment. E is what has always been modulus of elasticity. And I is moment of inertia. Right? So that is the relationship I want you all to denote. And we're going to do an example problem, at least one example problem that whoops out this equation. So I'm gonna put a square around it because you can indeed take that one to the bank. Actually, what I'm gonna go ahead and do, I'm gonna jump to that example problem right off the bat, because we'll have some other things to show you, but I want to make sure that you see how this applies. And I'm gonna pull out this example problem right here. And that is 12-1, right? I got it printed out right here on the screen. And I may need to change pins. Hopefully we'll see if it hangs out. It checks out with us the whole time. All right. So here's what it says. Here's what it says though. It says an L2 steel strap having a thickness of 0.125 inches and a width of 2 inches is bent into a circular arc of a radius of 600 inches. Determine the maximum bending stress in the strap. The maximum bending stress in the strap. So I want you all to make sure you pay attention to how this is being described, right? Because here's the picture, and the picture could throw you off. But it tells us that this strap, if we were to look at the cross section of this steel strap, cross section of it, it looked like a rectangle. And it tells us that the width of it is 2 inches, right? 2-inch width. And then it also says that it has a thickness of 125 inches. Right? So that is the steel strap. Now, with that being said, we're going to have to start off with our equation that I just gave you. 1 over rho is equal to M over EI. If we were to resolve this, right, for M, because M is what's going to unlock the maximum bending stress for us. If we were to rearrange this rather for M, we would write this equation as M equals EI over rho. So let's start things off by putting in what we know. What do we know about this, right? Well, we know that M is EI over P, and the bending stress equation is actually MC over I. Because there's no way for us to determine the actual moment in this problem, we'll be wise to take this equation for a moment and then simply substitute it into our maximum bending stress equation. So we can rewrite this as maximum bending stress is equal to EI over rho, put that in the parentheses, times C over I. Well, now we see that we have 2 I's here, and even though it would be quite simple to calculate the moment of inertia for this shape, we can go ahead and cancel out these I's and save ourselves some trouble there. So now we can just rewrite this equation. Maximum bending stress is equal to EC over rho. Now let's pay attention to what the difference is between EC and rho, right? Well, E, for starters, is going to be the modulus of elasticity of this material. What is the material? Well, the material says that it is a steel strap. So we know right off the bat that one number that I said you can remember in terms of properties, 29,000 KSI, you can go right there in terms of the E. Now, what is C? Remember what is C when we're talking about maximum bending stress? Well, C is the distance from the neutral axis of the structure that is bending, of the member that is bending. What is bending? Well, this is the cross-section of the steel strap that is bending. And if we were to assume they had a neutral axis down the center of it, which it does as a rectangle, C would be the distance from that neutral axis to the outer surface. And that distance will be half of 0.125, which is 0.1. Actually, am I getting it right? No. My calculator is not rounding. It's only showing me 1 decimal place. So the answer is actually 0.625. 625. I'm going to change this calculator definitely because I do not want it to mess me up anymore. All right. There we go. All right, so 0.625. So that's what's going to be our C. 0.625 inches. Now, what is rho? Well, the definition is the radius of curvature. One of the things that's actually helpful in this particular problem is that it tells us that this strap is being bent around this entire hoop here, right? It's being built around this entire hoop. And since that is the case, we don't have to imagine that it's around some imaginary circle. We can simply use this right here as that circle that we would have to imagine that I just explained to you. And therefore, the radius of curvature is the distance from the center to the strap. Now, they made an error in the book for this particular problem, and they put 12 inches there. So don't let that throw you off. It says in the problem that the circular arc has a radius of 600 inches. So instead of 12 inches, that should be 600 inches. That is definitely an error in the diagram, in the image. So rho, in this case, the radius of curvature of this particular steel strap is 600 inches. So now we have 600 inches, 0.625 inches, 29,000 KSI. And we can do the math on that right away to solve for our maximum bending stress. And if you were to do it with me, and provided that my calculator doesn't hold me to it, I'm going to assume that you should get 0.625. I got a decimal point off. I got a decimal point off. This shouldn't be 0.625. This should be a 0.0625. Please note that. Please note that 0.0625. And if that change is made correctly, then this should be an answer of 3.021 KSI. So this is 0.0625. Glad I caught that. Make sure you make that change correct when you go through it yourself. All right, 0.0625 will give you this value as our maximum bending stress. Get it? Got it? Good. That is 12.1. So that is going to be the sole example in this lecture that we'll do with this particular equation. But don't lose sight of what we just did there, right? We used it. We connected to the maximum bending stress by isolating M, plugging it into the bending stress equation, the flexural formula. From there, we make sure our numbers were correct. Make sure you use your decimals in the right place. And then we are able to solve for the problem. All right, so let's get to back to the concepts. Let's get back to the concepts. All right, gonna put that 12.1. And what I'm gonna try to do here is use a different writing utensil. I'm gonna use this little marker here. Hopefully it does a better job because I think my pen has run out of the ink. All right, so here's some things you need to remember. And I touched on this before in previous videos, but there's a relationship between, shear, moment, the load, as well as slope and deflection. So check this out, right? If you were to look at the moment, right, the equation for the moment, I told you that the moment, the way the moment changes over a distance according to X, that is, let me do this moment. Moment is the antiderivative or the integral of shear. And what that means is it is actually the second derivative, right? I'm sorry. That means that if you were to take the derivative of the moment, you would get the shear, big V of X. You get the equation for shear. And if you were to take the derivative of the equation for shear, what you would get is the equation for the load. Now, above this, before we even get to the point of recognizing that, shear is the integral of the load and the moment is the integral of the shear, we should know that if we were to take the integral of the moment, what we would then have is what we call the slope. And if we were to take the integral of the slope, what we would then have is where we first start. That is the deflected shape of the beam. So I said the deflected shape earlier. I said earlier, you can imagine that when a beam is bending, there's this exaggerated shape, right? Well, that shape is called the deflected shape, the shape that the beam physically goes into as it is experiencing the load, right? And we denote this as a function of X, or another way that it is denoted is by little v. So I'm gonna go back down again. So if we were to just have an equation that represented how that beam is now shaped, we would denote it as little v, or a function of X, That is the deflected shape. If we take the derivative, little b prime, or f prime of x, that will then give us the slope. The slope of that deflected shape. Y'all with me so far? Now, when you get down here to moment, what we are really doing now is actually taking the second derivative, and I'm gonna write it like this: d2 little v over dv squared. This is the second derivative of that v, and that is our moment. And because we sometimes want to know the actual value of it, we're multiplying this second derivative times these properties, which is E, a material property, and I, that is a geometric property. So we're going to say modular elasticity times moment of inertia times the second derivative of E is our moment. We're going to do the same thing down here. But instead of showing it as the second derivative, because we know that shear is a derivative of moment, what is it? If you said it is the third derivative, you are correct. Shear is the third derivative of the deflected shape. Down here at the load, again, if we want to know specifically what it is, we're going to do EI. And as you probably already guessed, this is in fact the fourth derivative of the deflected shape. All right, let me give you a procedure to keep in mind moving forward, a step-by-step approach. Step by step. Number one, visualize. All right, and by visualize, you're also going to draw an exaggerated shape. Shape of the elastic curve. Right? So elastic curve is another way of referring to the equation of the deflected shape. So the equation, the function, right, as a function of x is what we call the elastic curve. So that's the first thing you want to be able to do. You want to be able to visualize how is this thing even bending to begin with as a result of this load. Next, what you need to be able to do is establish the coordinates. Establish the coordinates for x, such as, positive going this way, right? And the coordinates for v, little v, right? The deflection, such as positive is going up. And if you have discontinuities where the load changes or there's a hinge or things like that, right? So if you have, this is 2 subpoint of 2. If several discontinuities exist, the coordinates let me do that because this big old marker is not going to help you out. Coordinates they may need regions. And by that, we basically mean that you're going to say, all right, this is for where x is, greater than this number, but less than this number. All right. So if this is a kind of a weird beam and you got changes in the way the loading or the beam is even constructed or presented to you, you may need to do some coordinates. Number 3, since EI right? In most cases, it's constant, right? So we're going to say, or if, since or if EI is equal to a constant, meaning that it's not changing. It's not changing. You're going to apply EI times the fourth derivative of little b to the load, W of X. Or another way to start, and this is where how you're going to begin your process, you're going to apply the second derivative, EI times the second derivative, V over D B2 to the moment. And I can tell you right now, this one is going to be way more applied, but you'll see what I mean when I say how you apply it, because what happens is you're going to have to start somewhere, right? You're going to visualize the elastic curve, but in order to get the equations, you're going to have to start somewhere. And one of the good places to start is by setting the second derivative, EI times the second derivative, equal to the moment, the equation of the moment. And you know how to do that because we've done that in our past chapters. And you'll see, we'll do it some more in this chapter too, so don't worry. Number 4, this is exactly what I'm talking about, actually. You're going to express the load, right? The load or moment, which is M sub X, as a function of X. That's what you're going to do. And you're going to do it, for example, going left to right. I hope this marker has made it better for you. It's definitely making me write bigger. All right, cool. So I have one more step-by-step rule I'm going to give you. Step number 5. Step number 5 is that you're going to find the constants of your function, the constants of your integration and the functions you're working with, using boundary conditions. Can be using boundary conditions. Now I'm gonna stay here on this sheet of paper and I'm gonna explain to you what that means, or what I mean by boundary conditions. So in other words, right, boundary conditions is what we're talking about now. If you have a roller at the end of a beam, let's cut that there. That means that V, which represents the deflected shape, when it is equal to 0, or V is going to be equal to 0, meaning there's no deflection happening whenever X equals 0. That's a boundary condition. So if you plug in 0 for X, the equation you have for your V, your deflected shape, should also be 0. That's one boundary condition. Another example of boundary condition is a pin, right? The boundary of this beam could be at a pin, right? And if that's the case, that means that the deflection is also still 0 whenever X is equal to 0. Another example of a boundary condition is, what if you have a roller in the middle of the beam? Let's say it's deflecting some kind of way on both sides, right? One of the things you can say here is, at that particular place, there's no angle being created, right, at this particular place. So you can say that V is equal to 0. Why? Because there's no deflection there. When the slope, and that's an angle right there, when the slope is equal to 0. It's another boundary condition you could use. And lastly, I'll show you this one. What if you have a fixed end? Well, at a fixed end, not only can you say that when x is equal to 0, b equals 0, you can also say that when the slope is equal to 0, v is equal to 0. Because at this very end, when it's a fixed end, you're going to have it come out a little ways. Let me see if I can draw that with a pencil. I don't want to mess up the notes. But let's say if you have a fixed end. Yeah, see that? And over here at the end of the beam, you have a load. Well, the deflected shape is going to actually come out a little bit and then begin to deflect. So at the very end of it, you're not going to have a deflection, nor are you going to actually have an angle happen. It's going to be flat. All right. Those are boundary conditions you're going to use. Another thing that you can use in addition to boundary conditions is something we call continuity conditions. Go ahead and knock out these concepts. Let's see. Conditions. Continuity. What that means is if you're coming from one side or you're coming from the other side, regardless of which direction you're going, the point at which the equations overlap or at the same point should be equal to each other. So if you have an equation for the deflected shape and x was from one side and it's a at a, the equation, if you're talking about the same deflected shape, but a different equation, v2, you plug in a, you should have the exact same value. Also, if you're coming from two different sides with your equation of the slope, you plug in the same number. If these equations are for the same beam, and they're accurate, they should be equal to each other. So what I mean by that is if you have a beam here, right? And let's say that you have a load on it. And because of the load, you have a deflected shape here. If you were to do an equation with A coming to the center of the beam for one equation, and that was 1, and you did another equation with going right to left, and that distance is A, you should get the same value at that location when you plug them into your equation. And the last thing I'll show you really quick is the symmetry conditions, right? These are all ways they're going to help you solve for the constants in your functions, the constants in your function. This is the symmetry condition. And what that basically means is, let's just say that you had this entire length of this thing being the length of L. Let's say that beam right here, still using this beam. This entire thing was the length of L. That means that if this thing is symmetrically loaded, symmetry, if it's loaded directly in the middle, and you have the same type of deflection on one side that you have on the other side, that means when x is equal to whatever the value is, that's half of L, that V does not equal 0. Why? Because V is the deflection, and it's going to deflect the most in the middle. So x at L over 2, V is not equal to 0. However, symmetry should tell us that when x is equal to L over 2, the slope, though, is 0. So they're saying that the slope of the beam, the tangential slope at the center of it, should be flat. Therefore, the slope is equal to 0. The slope. And if you think back on calculus, you will remember that the derivative of something is really the slope of the tangent line, the slope of the tangent line. So what we're asking ourselves when we take the derivative of our deflected shape and we come down to the slope, we're saying, what is the slope of the tangent line, the slope of the tangent line? So I'm bringing up my first, here we go. Yep. So the slope of the tangent line. So this right here is the slope of whatever this equation is, and it's the slope of the tangent line. So that means that for symmetry, if we were to take the slope of the tangent line right there at the center at L over 2, that value would be 0. So these are conditions. I'm gonna hold this right here. These are boundary conditions, continuity conditions, symmetry conditions that all should serve to help you solve for your constants in the example problems that we're about to do and your assignment problems. Let's do our first example problem now. First example problem is going to be 12-4. Technically our second example problem of the lecture. I'm going to keep working with this pen so that I can give you visibility. All right, determine the equation of the elastic curve beam using the x coordinate, excuse me, that is valid for 0, x is greater than or equal to 0, and less than or equal to L/2. Specify the slope at A, right? And the beam's maximum deflection. Maximum deflection. All right, so the first thing we're going to do here is we are going to look at the fact that we have to determine our reactions. We'll just jump to that right now, though. We'll say AY is obviously half of P, so P/2. And then BY is also P/2. BY is also P/2. So if we were to cut this right here, we're only looking at between 0 and L/2. If we were to cut it right here in that region, we would know that there is a vertical force P/2 here. We also know that, of course, there is a shear, and then there is a moment. And that moment is what would be our M of X. Let's not forget that the length of this is represented by X, right? Even as we see right there in the problem statement. So this is how you first start getting the equation for M of X. You're gonna sum the moments about the cut. Sum the moments about the cut. So if you were to sum the moments about the cut, and this was positive going this direction, we would have P/2 force times the distance of X, right? We would also have any other, well, P isn't involved, this P isn't involved in it. We would just have and that would be a negative. And then we would have a positive M sub X. So what that then means is, if we were to isolate that, M sub X is equal to Px/2. Does that make sense? That makes sense? This is an equal sign. Now, I wrote this as an equal sign because I want to remind you that M sub X is the second derivative of little v, of the deflected shape or the elastic curve. And it's not just the second derivative of it, but it's EI times the second derivative. Let's not forget EI in this whole process. So now we're starting things off right here, right? And it's asking us to find the beam's maximum deflection, So what we need to do in order to find the beam's maximum deflection is to remember the moment function's relationship to the beam's deflected shape. And looking back at this, we know that at moment, it's the second derivative. If we want to get a slope, we're going to take the antiderivative, we're going to take the antiderivative once to get the slope equation, and then we're going to take the antiderivative twice to get the deflected shape. That's what we're working towards to get the deflection. The deflected shape is what we're working back towards. So if we take the first derivative, which we know will be, the first antiderivative rather, which we know will be the first derivative of the deflected shape, v prime, it would be P x, this is calculus, y'all, squared divided by 4. Are we done? Is that it? No, because we have to do plus C. And because we'll have multiple C's, we're going to call that C1. That's the equation for the slope. Now, how do we get the equation for the deflected shape? Well, obviously, we take the antiderivative again. I'm sorry, that shouldn't even be there, right? It's just going to be V. It's just going to be V. V is P x to the third divided by 12 plus C1 x plus C2. That's the deflected shape. Let me put that in the parentheses. Let's say deflection. And because we're still trying to incorporate EI, right? Let's keep EI out here. These are constants, so they're not going to affect how we're doing our antiderivative. We're just going to keep it over here. So there's our equation for the deflected shape. So now what do we do? In order to get these constants C1 and C2, we're going to have to use a boundary condition that is true for this part of the equation. Well, what do we remember about our boundary conditions in this part of the beam? Well, we know that for a pen, B equals 0 when X equals 0. And that's what we can work with here. So we'll say, here's how you can write in your own paper. When X is equal to 0, excuse me. When X is equal to 0, the deflected shape should also be equal to 0. So we're going to use this entire equation here. We're going to set it equal to 0. So the deflected shape is equal to 0 when P times plugging in 0 for X to the third over 12 plus C1 plugging in 0 for X plus C2. So now this cancels out. This cancels out. And what does that then tell us about C2? Well, it tells us that C2 is equal to 0. Make sense? That was a pretty easy boundary condition. What is another one we can look at from our boundary conditions? Well, we know that at L over 2, our symmetry conditions, when X is equal to L over 2, the slope based on symmetry conditions is equal to 0. So what that means is, using this slope equation, we can set that equal to 0 because this is what the boundary condition says. Set this equal to equation where P is not times 0 because we're plugging in L over 2 for P. It's L over 2 squared over 4 plus C1. Now, if we isolate C1, what we will find is, obviously, we're going to square that. That's going to be 4. 4 is going to come on there. That's 16. C1 is equal to a negative P L squared over 16. So now we have our constants here. You know, C2 is equal to 0, so we don't have to worry about that anymore. And then we know that C1 is equal to negative PL over 16. Are we done yet? No, we are not done. That just gave us our constants for these equations. So we're going to go back and write our full equations, right? We can write our full equations as so. Our full equations are, for the moment, EI second derivative equal to PX over 2. We found that out at the very beginning. Shear equation, that's going to be EI I'm sorry, not shear. That's not what we're looking at. We're going backwards. We're looking for the slope. The slope is EI V prime, right? Or we could say EI dV over dV over dx, but we'll say V prime is equal to px squared over 4, right? That's what we got here. Px squared over 4 plus C1. And so we're going to write this instead of C1. So we'll do plus negative P L squared over 16. That's the slope. And then the deflection equation is EI V is equal to Px to the third over 12. I'll go ahead and just write it as a minus PL over 16. Let's not forget our equations. I'm taking this directly from what we just got, right? Px cubed over 12 plus C1 times X plus C2, which we already determined to be 0. So we really don't even need to write that. So those are our actual definitive equations for the moment, the slope and the deflection. But the problem asks us something that we still haven't arrived on yet. It says, specify the slope at A and the beam's maximum deflection. Well, let's start with the slope at A. The slope at A means we're going to plug in 0. We're going to plug in 0 into all the x's for the slope equation. And what that would give us is that we'll remove that. And we're going to go ahead and include EI. So the slope equation can be written right here, like that. That's a theta. If you plug in 0 here, that's going to be gone. So it's just going to be this term right here, and we'll divide EY by both sides. So the answer to that is P L squared 16 divide EI by both sides, EI. This, my friends, is the slope at A. That's the slope at A. Of course, if we had the number of what L was, we had what P was, and we knew the material, we could actually get a number. We could actually get a number. But this is the equation. That's the slope at A. And then we need to know about the maximum deflection. Well, looking at our problem, just looking at our diagram, where would the maximum deflection take place? Well, we already discovered that this is a symmetrical beam. So the maximum deflection is going to be right there in the middle at L over 2. L over 2. So we're going to take the deflection equation, and for all the x's, we're going to plug in L over 2. We're going to plug in L over 2. All right. That's what we're going to put there. And if we were to do that, x equals L over 2. We'll write that right there. Here's what this equation would look like after you divide both sides by EI. Px (48 over EI) on parentheses of 4x squared minus 3L squared. That's the equation of deflection at L over 2. At L over 2. Let me put a square around that. Now, one of the things you'll notice that I actually did an intermediate step here because I still didn't plug in L over 2 for all of my x's here. So here's what V max. V max would be equal to negative P L to the third all over 48 EI. Right. So this right here is just a simplified version of what we have here. We got a common denominator of 48 between these two, and we divided EI by both sides to get that. Now, when we plug in X equal to L over 2, we're able to get our maximum deflection here, which is what the problem is asking us for. There's a lot of steps, a lot of maneuvering, a lot that you have to pay attention to, algebra as well as calculus. But I'm confident you all can figure this out. Definitely learn it. We're going to do some more examples. We're going to stay on this chapter in the next couple of videos as well. So see if you can go through this example again on your own. Give your best shot, and I'm sure that you will begin to understand it more and more as time goes on. All right, I'll catch y'all in the next lecture. We're going to do another example problem like this when I see you next time. All right, peace.